Okay, so our next talk is about Hamiltonian simulation on a quantum computer, and Guanghao Lo is our speaker.
All right, thank you for the introduction. So today my talk will be about optimal Hamiltonian simulation, an algorithm that you can run on a digital quantum computer. So this is work done with my advisor at MIT. So let me quote what John Fresco said earlier this week. Whatever you say about quantum information or processing is a statement about physics. I really like this because I think that the converse is also true. Whatever you say about physics is a statement about quantum information and processing. So in this talk, we look at very simple physics, take it as far as we can, and see what kind of statement it makes about quantum processing. And this statement is quantum signal processing, which when applied to the Hamiltonian simulation problem, turns out to be a very nice final ingredient that closes the gap between upper and lower bounds in the query model. So the connection between physics and computation is very well known. For example, physical concepts can inspire general problem-solving methods. For example, you have adiabatic evolution and quantum walks. These are universal for quantum computation, but compiling any specific algorithm to these architectures can lead to very large overheads or sometimes even wipe out the polynomial improvements, which means that they are not really practical for the quantum computers of today. So an alternate approach has arisen, which is to use physical systems directly to solve computational problems. For example, we have boson sampling, which computes the matrix permanence using a physical system of linear optics directly. And we also have recently more innovative methods for Hamiltonian simulation by directly implementing your desired Hamiltonian in a physical system. So this is the analog quantum simulator. These physical approaches to computing are very elegant, they are very simple, and they are very fast because they make a direct connection to the problem you're trying to solve. So as a result, they have very small overheads, very small constant factor overheads, which means that they are actually candidates for very near-term quantum computing devices. However, one issue that they face is that they are not quite as scalable as a universal quantum computer because they are hard to make fault tolerant. So we would like to merge the best of these two worlds. We would like to still maintain the very small constant overheads of exploiting physical systems to perform computations, maintain the intuition of how they perform, which aids our understanding of how algorithms work. And in doing so, perhaps the final algorithms will be simple and very fast. And we would like to also perform this map in a way that is compatible with fault-tolerant quantum computation. So this is the idea of quantum signal processing, the abstraction of physical dynamics into a computing module, which we call a quantum signal processor, that allows us to do all that. So now I'll go on to the outline of my talk. I'll briefly talk about what the Hamiltonian simulation problem is and previous work on this field. I will then give an overview of the quantum Hamiltonian simulation algorithm that we have invented and how quantum signal processing applies to it. And then I'll conclude. So the Hamiltonian simulation problem is a very simple question. We have a description of a Hamiltonian of a quantum system, and we would like to simulate its time evolution operator. So what this means is that we would like to implement the time evolution operator, a unitary, on a quantum state with small error. So this is a very useful and important question because nature is based on physics. If we can solve this problem, we can, say, simulate chemistry, materials, maybe more ambitiously simulate the Big Bang. It is also a very common primitive in many quantum algorithms, and some algorithms are naturally expressed as a time-independent Hamiltonian, such as quantum walks and span programs. So by now, you've probably seen this quote by Richard Feynman about 4 times, but that's because it's a really good quote. The Hamiltonian simulation problem is hard because nature isn't classical, nature is quantum. One intuitive way to understand why it is hard is a curse of dimensionality. If you have n qubits, the number of parameters you have to track in your state space scales exponentially with the size of your system. Moreover, the Hamiltonian simulation problem for time-independent Hamiltonians is universal, and so if we could solve this on a classical computer, I think we would need to find new jobs. All right. So the difficulty of implementing this time evolution operator on a quantum computer very much depends on the assumptions we make on the input. For example, if our Hamiltonian was still presented to us as a list of exponentially many classical numbers, a quantum computer wouldn't help. We either need a description that is sparse, so polylogarithmic number terms in the dimension of the system, or we need a quantum way to specify a description of this Hamiltonian. So there are a few major input models. The first workable algorithm for Hamiltonian simulation was by Seth Lloyd. There he considered Hamiltonians that can be decomposed into a sum of local interactions, where each local interaction is easy to simulate and only acts on a constant number of qubits. This very naturally describes many physical systems and provides an intuitive way to see how Hamiltonian simulation can be done. So using well-known product formulas such as trottlerization, we can simulate time evolution of the sum by a product of time evolution of the components. And as we have more exponentials, the error goes down, but so does the time of simulation go up. So this was generalized with the d-sparse Hamiltonian model, where we have a Hamiltonian which is a matrix of numbers, and there are at most d non-zero entries in every row. So this can be related to the previous model when d is depends on k in that formula, proportional to the number of terms and exponential in the dimensionality of the support. So since this now could in principle contain exponentially many numbers, we need a quantum way to provide information on this matrix. This is commonly done by assuming access to oracles that compute the positions of non-zero column indices and also another oracle that provides the value of these non-zero elements. So one reason why this is a popular model is because it is commonly used in the design of quantum algorithms based on quantum walks and can sometimes be used to claim exponential speedups when d is polylogarithmic in a dimensionality, such as in QRSP for matrix inversion. A more recent model introduced is the unitary access model, where instead of a sum of local interactions, where each interaction is a Hermitian matrix, we have a Hamiltonian that is a linear combination of unitary operators. This requires a different oracle, but is notable because it does better than all of the product formula approaches used for k-local interactions, and is very promising for the simulation of physical systems. So let's look at some of the prior work that has gone into this, a brief history of simulation. We all knew that the Big Bang began in 1982 because that's when our career started with Richard Feynman. And after the Dark Ages, lasting about 10 years, Seth Lloyd came up with the first workable quantum simulation algorithm. So you can see here that it scales polynomially in the number of terms m, and the error, and also the time. So this led to an inflation of many new approaches to simulate Hamiltonians, where you have product formulas that increase the scaling with respect to sparsity, time, and error. And in the last result, in 2010, we see how additional structure about Hamiltonian can be incorporated if you know more about it. Like say if some of the components have a larger norm than the others. So this was further improved by the unitary access model, which, while it doesn't quite use the same inputs, achieves much better scaling than product formulas. And so it's something that has been developed quite extensively in recent years. In parallel, techniques for simulation sparse Hamiltonians have also steadily progressed. And you can see that the scaling of query complexity has improved with respect to the sparsity d and the dimensionality. So it has gone from poly and d to d4 and d cubed. And the dependence on dimensionality is log star, which is basically a very small constant factor. All of this was improved by one breakthrough result by Andrew Childs, where he designed a quantum walk applicable to any Hamiltonian. And by just using, and by querying the d-sparse oracles, he achieved optimal time scaling in both optimal scaling in both the time and sparsity, but unfortunately the scaling with respect to error is significantly worse than the product formula approaches. So now we enter the modern era, and the breakthrough result in the last 2 years was by Dominic Berry, Andrew Childs, Richard Cleave, Robin Kutharia, and Rolando Soma. So there they found an alternate approach for the d-sparse model that has optimal scaling and just error. But unfortunately, the scaling with respect to time is not quite linear, but very close. This was similarly generalized to the unitary access model. And more recently, they had a paper achieving nearly optimal dependence on all parameters. There, they achieve a scaling that's the product of time and something that's basically logarithmic and error. So this is just a multiplicative factor away from the lower bound, which they also proved in that paper. So last year, we finally managed to close the gap between upper and lower bounds. We still use the same ideas of the quantum walk developed by Andrew Charles, but we use that as a subroutine in our quantum signal processing module. And this turns out to be the final ingredient to close the gap between upper and lower bounds. So our approach is somewhat more specialized than the techniques used by previous work, but we managed to generalize it more recently to the unitary access model with an input model that can deal with these two oracles as special cases. In parallel, Dominic Barry and Novo, they further refined their techniques to achieve scaling close to the lower bounds. So note that their scaling is slightly worse, but their ideas have merit because, in a sense, their techniques are more flexible and could be applicable to other problems like time-dependent simulation. So now let's give an overview of how our algorithm works. We consider the D-sparse input model. We will not be talking about qubitization in the rest of this talk. In this input model, we assume access to two oracles. We have the column oracle, which if you feed in the row index I and a number L, spits out the alpha non-zero column index, the alpha column index of the alpha non-zero matrix elements. We also have another oracle, the element oracle, that on feeding in a row and column index spits out the matrix element of your Hamiltonian. The goal of this is to output the time evolution operator, and our algorithm works by first implementing the discrete time quantum walk for any Hamiltonian invented by Charles. So this quantum walk is very nice because using just a constant number of queries to these oracles, it implements exact time evolution, but with a Hamiltonian that has a modified spectrum from the desired Hamiltonian. The difference is by a function arcsine, so we want to linearize this. We do so using our quantum signal processing techniques, where we find a physical system that very naturally solves the problem of eigenphase transformations. And so if we were to implement an eigenphase transformation by a sinusoid, composing arcsine with sine results in identity, and so this linearizes the time evolution operator and gives us our desired simulation algorithm. And since the quantum walk takes a constant number of queries, the query complexity of this final approach is entirely dependent on the quantum signal processing module. And this query complexity turns out to be linear in time sparsity, the maximum absolute value of any entry in your matrix, and is additive with the desired error of performing this transformation. So because earlier on I claimed that physical systems, they are, in a sense, closer to the computational problem with smaller overheads, so maybe they are simpler, and this turns out to be the case. We only use a single ancilla qubit, which means that this could be a very good candidate for a small quantum computer. So how does this work? I claim that we use very simple physics, and what could be simpler than a single qubit unitary? So here I have a single qubit rotation. You could visualize it as a rotation of the Bloch sphere about the x-axis by some angle theta. And as you change angle, you implement a different gate. So how can you use this to compute? I think the answer depends on who you ask. If you were to ask somebody who works on quantum computation, they would say, let's choose theta and perhaps implement universal discrete gate set like Ix, and with perhaps other rotations, the Hadamard and T gate. Somebody who works in quantum metrology might think, perhaps we could apply this to a state and compute an estimate of theta. That's a form of computation. And somebody who works on quantum control might also wonder, well, do we have the flexibility to really choose the rotation angle or the input state? So here we combine all of these ideas. Really, this is just a restatement of the definition of a unitary matrix, but I think it's worth phrasing it this way. The single qubit rotation is a computational module that computes some function, some unitary function that depends on the input parameter, which may or may not be under your control, the input state, and the measurement basis. So to give an example of what this means, let us multiply a bunch of these rotations together and apply it to the 0 state and project onto the 0 state. So this computes a function cosine n theta, which I've plotted there. This seems like neat, but it doesn't seem very useful. Sinusoids, like, all right, I guess they're there, but what could you do with it? So clearly, if we want to use this to solve interesting problems, we need to be able to compute interesting functions. We do this by assuming that we can introduce more control parameters. So let's sandwich our x rotation about 2 phase rotations, which we have control over. So now if we consider a sequence of these single qubit rotations for some choice of phases, we see that they can compute more interesting functions. So there I've plotted 3 different functions for random choices of phases. And you could maybe imagine that with some good choice of phi, you could do something really interesting, like compute the thresholding function, or maybe compute a spike function. So the idea here is that our single qubit processor is a string of unitary functions, and our control parameters, the phase, is like assembly code that we run on this processor to compute a unitary function. Since this is a single qubit unitary, we can decompose it into the Pauli basis, and the coefficients there are functions that we would like to design. And we can then select the desired functions or their linear combination by some appropriate choice of input state and basis measurements. So, this seems interesting, maybe, but maybe it might be obvious. Why is this a hard problem, or why haven't anybody done this before? This is because it is actually very hard to design this. The best analogy is with the single qubit gate synthesis problem. So until, say, 3 or 4 years ago, single qubit gate synthesis could only be solved in exponential time if you wanted to find an optimal decomposition into a basis discrete gate set. So there you have a matrix of numbers, your unitary matrix, and you want to decompose it into a string of other matrices. The single qubit processor considers a modified variant of this question. We instead have a single qubit unitary function. So this is not a matrix of numbers, it is a matrix of functions. And we want to decompose it into a basis set of unitary functions rather than unitary gates. And this is a control sequence that has been studied for decades in fields like NMR. So we have built up a massive amount of intuition on what we could possibly do with it. But designing an optimal sequence has often been an exponentially hard task because the best algorithms essentially amount to doing a best fit to your target functions by gradient descent. So recently, we solved this problem by finding necessary and sufficient constraints on various choices of these functions. So what we'll focus on today is designing the coefficients of the identity and the x Pauli terms. And the constraints on what we can choose for these functions are actually quite intuitive. When our matrix, when our rotation angle is 0, we implement an identity rotation. So a sequence of identity gates is just identity. And that means that the coefficients of the identity operator must be 1 at theta equals to 0. And similarly, probabilities must be bounded, so the sum of squares of any of these terms must be less than 1. And if you perform a direct expansion, you find that A and C are no more than a Fourier series. So this is quite cool, because the Fourier series, they form a complete basis for real functions on bounded intervals. So in principle, you could approximate or implement any arbitrary function you want with a sufficiently long sequence of single qubit gates. And we also provided an efficient algorithm to show how we can compute in poly n time the synthesis of a single qubit function into its component gates given some Fourier series A and C. So now we have a systematic methodology for actually doing something useful with the single qubit processor. But it is not clear how this is applicable to general quantum algorithms. This is a single qubit operator. Quantum algorithms, interesting ones, are multi-qubit operators. The first obvious step would be to perhaps find quantum algorithms that are naturally isomorphic to SU2, but these are limited or perhaps not as exciting. For example, Grover search is one of them. So the solution to this is to recognize that we are not interested in literally applying this. We are interested in treating this as an abstracted quantum computational module. So we'll instead use this and try to expand its utility by, say, appending it to a larger system. So let's consider an ancilla state that is a single qubit and a system state that could have many qubits. And let's put our single qubit processor in the ancilla states. So usually when you have an ancilla in a system, you would think that the ancilla controls the system. Here we take a different interpretation. The single qubit rotation operator is controlled by our system, meaning that the angle of rotation in each of those primitive rotations depends on the state you feed into the system. To see how this is possible, let's look at an arbitrary unitary matrix W with some eigenstates lambda and some eigenphasors. And let's look at the controlled version. We create this controlled version where if you feed in a plus state to the ancilla, you get identity on the system, and if you feed in minus on the ancilla, you get the eigenphase. You get W on the system. So when you feed in an eigenstate, you decouple the two. The eigenstate remains unchanged, but in the single qubit line, you have implemented your single qubit rotation. So now let's replace all of those rotations about the x-axis by this controlled W rotation. And now we find that if you feed in an eigenstate, the single qubit processor, if you apply it to the plus state in the ancilla and project on the plus state, amounts to applying a function on the eigenstate lambda. So this is like changing the coefficients of lambda. And the value of this coefficient depends on the eigenphase of lambda. So now you can kind of see how maybe this could be used to perform eigenphase transformations. We can choose the real and imaginary components of this coefficient to perhaps match a complex phase factor that depends on the rotation angle theta. And how do we do this? Let us choose some objective function for our eigenphase transformations. So this is h theta. It is a periodic function that maps a circle to a circle. And we want to approximate this complex phase factor with a complex Fourier series of degree n. So n will determine the number of single qubit rotations, and in turn determines the number of controlled W's, which in turn determines the number of oracle queries to our element and column oracles. So this pretty much entirely determines the query complexity of Hamiltonian simulation. So the first step is to find a good approximation to this complex phase factor. So you find two Fourier series that approximated to some error epsilon. In general, some choice of this approximation may not satisfy the constraints which I presented earlier. For example, perhaps it could square to be greater than 1. But it's easy to compute from these an achievable modified set of functions that still approximate the phase factor to only a slightly larger error, but it's achievable. So now if we substitute these transformations into the coefficients, we see that by applying this single qubit processor, but with rotation angles controlled by the system, we can implement on eigenstates our desired eigenphase transformation. The query complexity of this depends on details of the target function. For example, if the target function is smooth, you get a polynomial scaling of error. If it's analytic, you get exponential error. And if it's entire, you get super logarithmic error. The target function for Hamiltonian simulation is an entire function, which is why we get the scaling that we see, because the query complexity for any target n is very good. So as you can see here, this approximates the desired phase factor with a trace distance that depends on the initial error of your approximating Fourier series. And because the phase factor has a norm of 1, if your Fourier series approximates this, its success probability is also close to 1. So now let's apply this to Hamiltonian simulation. The objective function for Hamiltonian simulation is a sinusoid, because this linearizes a quantum walk. There's a very well-known Fourier series expansion for this objective function. It's a Jacobi angle expansion. And it is well known that if you were to truncate the Fourier expansion and only keep the first n terms, you get essentially the best approximation. So by doing so, you can compute the approximation error by summing over the terms you did not consider. And because this is an entire function, the scaling with error is super exponential rather than just exponential. So this allows us to solve for the query complexity as a function of the simulation time tau, which you see in that. J is actually a Bessel function, and the target error. And this query complexity matches lower bounds derived by the authors there for where they got it by finding a time-independent Hamiltonian that solves a parity problem. So you can see that the error scaling before solving for n of the quantum signal processing procedure and that of the lower bound are very similar. They only differ by a factor of e over 2 inside that, below that exponent. And actually, if you were to evaluate the truncation error numerically, that constant factor disappears. So that's pretty cool, because this is an algorithm that appears to also be optimal up to constant factors. So one might think that by solving the query complexity of d-sparse Hamiltonian simulation, we have kind of ended the field, but that's hardly the case. We are more like in a big grip of Hamiltonian simulation where the number of questions are rapidly expanding. There are many open problems remaining. For example, we have solved query complexity, but what really matters in the end is the gate complexity of simulation to determine whether it's practical. There are also other interesting questions like time-dependent simulation, which our technique doesn't handle well, but the techniques by Dominic Berry and Novo could do. And we also have the simulation of open quantum systems, which is very interesting because all quantum systems in nature are open. So there was some very nice recent work in the poster sessions earlier this week that dealt with this. And also very nice work for Hamiltonians where you are given more a priori information about their structure. For example, whether the sum of whether their terms commute rather than just having a list of Hamiltonians with no other information. So another very interesting direction which could be realized in the near future is analog simulation, and there will be a very interesting talk, I think, by Stefan Paddock later today afternoon. There are people who came out last night, and I think it's exciting. So we also introduced this new query model for Hamiltonian simulation that apparently deals with the d-sparse input and the unitary access input. So perhaps this could be used to solve other interesting input models that allow us to realize quantum speedups by phrasing the problem differently. So in conclusion, I hope I've convinced you that we have a field that is interesting and actionable, that arises by combining ideas in quantum metrology, control, and algorithms. Control arises because we choose a control policy to implement some desired unitary function. Metrology arises because we select the components of this unitary function with some choice of states and some measurement basis. And algorithm arises because we treat this unitary evolution directly as a computational module. So together, we have looked at what happens if you take a single qubit system and abstract it this way. So very natural questions would be, what if we were to look at more complicated systems like 2-qubit interactions or analog simulators? What problems would they naturally solve if you were to just look at their dynamics? And so since I quoted John Fresco earlier, but there haven't been any black holes for this conference, I have a black hole over there. And maybe you could think about what kind of quantum information processing would we be doing if we had control over a black hole, say by jumping in every now and then? What problem would this solve? And maybe it could lead to some deep insights about how we relate physics and computation. So if you're interested in some of the ideas that went into this, I have other work down there that focus on the results related to the qubit processor. And if you were to look at them, I'd be very happy. All right, thank you.
Okay, so we have lots of time for questions.
Okay, thank you. So I guess maybe different from some of the previous algorithms on quantum simulation, I guess your algorithm requires some kind of classical computations, like computing the angles for the rotation operators, right?
That's right.
Yeah. So I guess in practice, such kind of calculations might be carried out numerically. So I guess I just wonder, do you have any feelings of the performance of such classical calculations?
So the nice thing about these classical calculations is that we only need to perform them once. So if you wanted to simulate the Hamiltonian for any time t, you would compute the string of phasors, and for any other Hamiltonian simulation problem, you could use the same string of phasors to simulate for the same amount of time t. So in any case, the computation can be done in polynomial time. So this is just a classical overhead that we just need to do once. It's easy and not need to worry about in the future.
Other questions?
can you give us a natural system which is described by a sparse Hamiltonian?
So I mentioned k-local interactions earlier. They describe many physical systems because most physical systems are local. And you can always describe a k-local system with a d-sparse Hamiltonian. And because your k-local interactions only acts on a constant number of qubits, the sparsity is going to be bounded times the number of terms in your local interactions. So that's a natural system.
Okay, I see.
It's possible I'm confused. Your result is about query complexity.
That's right.
So, but you also talked about overhead and implementing it on a small quantum computer. So,
right.
So, how would you implement the oracle if you were doing this as an actual?
That's an excellent question. I guess I forgot to mention the caveat. It is an extremely small overhead beyond the complexity required to implement the oracle. Some oracles are easy to implement, some oracles are hard. This is actually a very active field of research. Every now and then you see papers talking about implementing various sparse oracles. This is why the unitary access model is so appealing, because the oracles are very simple physical rotations rather than being composed of some large sequence of single and 2 qubit gates. So the unitary access model is a great candidate for realizing on a small quantum computer, and our techniques can now deal with that.
We still have time for more questions. Nathan.
So one of the things that you were discussing is the inability of this method to simulate time-dependent Hamiltonians, which is inherited from its sort of legacy of being based in quantum walks. So I was wondering if you could talk about, how you, specifically why this is a problem, and if there's potentially any way forward to address it.
All right. So we live in a universe that's quantum mechanical, and our universe may or may not be closed. It's probably closed because maybe at some point you get to a large enough scale where everything is closed. But nevertheless, we are still interacting in a time-dependent way, like in this conference. So clearly, there is some way to encode meaningful time-dependent interactions in a time-independent Hamiltonian. And this is an idea that has been explored a lot in thermodynamics, for example, in autonomous heat engines. And I think there's a deep link between Hamiltonian simulation in the time-dependent case and quantum thermodynamics.
Here. So for single qubit gate decomposition, we know there's a Solovay-Kitaev algorithm. So your algorithm for the single qubit gate decomposition, is it exponentially better than the Solovay-Kitaev algorithm?
They are incomparable. The Solovay-Kitaev algorithm can be applied to the single qubit function synthesis problem, but only in a very restricted case. So the other application of Solovay-Kitaev is for synthesizing a single qubit gate from a discrete gate set, and that's a different problem. Basically, you can't really apply Solovay-Kitaev to the question we consider here of a general way to synthesize a unitary function from a unitary basis set of functions.
How about this? Do you have some intuitive explanation how the scaling with the epsilon is a polylog?
Right. Let's look at, I think this is related to deep results in pure mathematics and approximation theory. I don't really have a good intuitive explanation why, but the math just says that when your functions are smooth, you can approximate it better with functions that vary. And when your function is really, really smooth, like analytic, you can even more easily approximate it by functions that vary, such as sine waves. And so the smoothness and analyticity determine how the error scales with the number of terms you use to sum up to approximate this function. I think that's the best answer I can give.
So Thanks again for a second question. One of the things I'm also kind of curious about is, of course, your algorithm ends up scaling with the max norm of the Hamiltonian.
That's right.
So if you're putting this forward as an approach to simulate physical systems, how would you go about simulating something like the Coulomb potential?
There are a few important differences between that problem and the d-sparse problem. The first issue is that the Coulomb potential acts on a continuous basis of quantum states. So there we would first need to find a way to reasonably truncate this real space approximated with a discrete basis. Maybe that could be a way to do so that does this with small error, but maybe you couldn't. But let's suppose that you could. Then we would need to think about how you could approximate unbounded operators with say, d-sparse Hamiltonian, and these unbounded operators will have very large max norms. So maybe the solution here is to find a different basis where maybe the Coulomb potential can be easily separated into low energy and high energy components. And this is why I think the recent paper for the talk later on analog simulation is interesting, because they describe a method to perform such a splitting of high energy and low energy subspaces.
Okay, let's thank Guanghao again for a great talk.